So we can look at a couple special cases, and these. So right now, we, being you and us, and in your standard location where you are in your undergraduate career, you don't really have the ability to solve that type of partial differential equation, at least not yet. And at this point for our course, we're not that interested in. We want to look at some special cases, and both of these happen to be steady state. Now we are, in a couple weeks, going to come back to the heat equation, and we're going to say, all right, well, how do we solve the transient portion of it? But for right now, we're going to look at the steady state forms. So we can look just straight at the straight steady state form, which makes it equal to 0, but I leave the energy generation term in. Or the even easier or more straightforward cases, we say, all right, let's turn off any possibility of energy generation here, and this becomes our ordinary differential equation. Now, that might look familiar, but let's do a little bit more with it, right? So we have the second spatial derivative, but of course, let's rewrite what the second spatial derivative actually is, right? That says you have a function t as a function of x, take the first derivative of it, and then take the derivative of that. So what we're saying here is that the derivative of some quantity is going to equal 0. So the derivative of what yields an answer of 0? Well, the derivative of a constant is equal to 0. So that's going to tell us that dt dx, the solution, or the derivative of t with respect to x, is a constant. And this, ladies and gentlemen, that is a straight line, right? dt dx equaling a constant means that the slope is constant. So we'll come back to that in a second, but let's go ahead and talk about boundary conditions that we're going to apply to it. So the first type of boundary condition is where we would specify the temperature of the boundaries. Now again, I've mentioned this, and we're not going to worry about the mechanism by which we're specifying and holding these surfaces at a set temperature. As I said, might have to use a heating jacket and a cooling jacket that we can somehow maintain the temperatures perfectly. But this is more of a thought experiment. So if I somehow have some mechanism to keep the left-hand wall at some value t1, so x equaling 0 for all time. So I'm leaving so this is t as a function of x and time equals t1. So I'm evaluating this at x equaling 0, right? That's my boundary, my left-hand boundary, and I'm going to say that it's going to be t1 for all time. And we're going to do the same thing on the right-hand side. So this second boundary condition, right? It's second order spatial, so we need two boundary conditions. So on the right-hand side, where x equaling L, again for all time, we'll specify a value of t2. And those would be my two boundary conditions. Now, the second type of boundary conditions is, instead of specifying the actual temperature of these surfaces, I can specify the flux, the heat flux on these surfaces. And the heat flux is given by Fourier's law. So notice that I'm leaving explicitly the A out. So I could put A in, but we're doing this as more of a more general problem. So what I'm assuming here is that this volume, this slab, this material is infinite in this direction and infinite in and out of the board. Of course, we don't need to have them infinite. We could then say, well, we may have a smaller slab with perfect insulation around its perimeter. But in any case, we're only allowing heat transfer to move in the x direction. So we'll say, we'll use Fourier's law, evaluated at x equaling 0, and that would give me the heat rate that's passing through the left-hand wall at x equaling 0. I would use the same value of Fourier's law, and I would evaluate it at x equaling L, and that's going to give me the heat rate that's passing through the right-hand wall. So there's another set of boundary conditions. And of course, we can mix these boundary conditions. I could say that this wall is a constant temperature, and this wall has a heat flux on it. So these are things that we'll be looking at when we look at actual problems. So now, we're still in the type 2 boundary condition, but there's some variations that we can look at it. If this surface is next to or is completely insulated, we do not allow for heat transfer across this boundary. So the heat flux, Q dot, is going to be equal to 0. So in that case, that would be 1 variation of the heat flux boundary condition. On the right-hand side, or the other side, we could allow that the rate of heat transfer is going to be exactly matched by a convective, I guess I can call it a convective boundary condition, but it's going to be defined by the convective situation that exists outside the wall at x equaling L. So to utilize this, we would typically you would need to be specified what the heat transfer coefficient is, H, and what the infinity temperature is. But again, we'll be taking a look at it, but it's just two variations on how we can utilize the heat flux as terms of a boundary condition. All right, so I just want to quickly go through one example. This is an example from another textbook, but I do like this type of example because it allows us to sort of manipulate what the heat diffusion equation is to a certain extent. All right, so what we're being told here is that the temperature distribution across the wall that's 0.3 meters thick at a certain instant in time. Now that's important. When you hear a term saying at a certain instant in time, the implication is that something will be different at another instant in time. So what they're implying here is that this is an unsteady problem. But we can still utilize the heat diffusion equation. Well, the heat diffusion equation is inherently for the unsteady process. Let's see where this is going to take us. It tells us that the temperature distribution is this quadratic. A, the constant, is 200 degrees C. B, the linear term, is minus 200 degrees C per meter. And of course, you're going to multiply it by meter, the x value. So this is again going to have the units of degrees centigrade. And the quadratic term is 30 degrees centigrade per square meter, which again, you're going to be multiplying by a square meter. So that makes perfect sense, right? The temperature field has the units of degrees Celsius. So what I'm going to do over here is this diagram is the diagram of the actual physical situation. So it's being plotted from x equaling 0 to x equaling 0.3. I'm evaluating the temperature at x equaling 0 using this equation, and I get 200 degrees C on the left-hand side. And on the right-hand side, I get the value of 142.7 degrees C. So this is just a cautionary to you. So a lot of you would say, oh, it's quadratic, and automatically you see a parabola in your head. But what we're finding out here is we're actually on, right, it's parabolic, right? It's the C term's positive. So it's a upward parabola, but we're way over on the left-hand side, way far away from the minimum of the equation. All right, so what we see is that it's almost linear, but it's not linear. So now I've put these in a priori before I've evaluated them, but what I'm assuming here is that when I evaluate Q in or Q dot at x equaling 0, I'm going to get a positive value. So the heat's coming into the left-hand wall. I'm also drawing the heat flux on the right-hand wall as being also going from left to right. So in this case, I'm also assuming it to be positive, but a positive value for the heat flux at the right-hand wall means that we're having heat flowing out the right-hand wall, which of course will make sense because look at the heat profile. We're expecting a heat profile where energy is kind of flowing downhill. So this is our equation. If I take the first derivative of it, it's going to be minus 200 plus 60x. And of course, it's dt, right? So the numerator has units of temperature, degrees C. Denominator is dx, so units of meters. And now I can evaluate, if I know dt dx, I can evaluate the flux using Fourier's law. So minus K. K is 1 watt per meter per Kelvin. And here is the term dt dx, right? dt dx now is an actual function. And if I evaluate it, my degrees C, right, this is a temperature differential. So degrees C and degrees Kelvin are going to cancel out. I'm actually going to come back to that tomorrow in class. This can actually be a little bit confusing for you, why I can cancel these two out. So I have a little explanation that we'll do in class. And this will end up with watts per meter squared. So 200 minus 60x, watts per square meter. And the question is this a steady state situation? Well, we don't think so, because we know this isn't linear, even though it's almost linear, and we have this hint that at a certain instant in time, it's implying that there's something happening with regards to time. All right, so let's go back. Let's go take a look now. So if I evaluate, here's my expression for Q dot as a function of x, 200 minus 68 watts per square meter. If I evaluate this at the left-hand wall at x equaling 0, I'm going to end up with 200 watts per square meter. So the left-hand wall, right, and this is positive, so the left-hand wall, Q dot in, is 200 watts per square meter. The right-hand wall, if I evaluate it at x equaling 0.3, evaluates to a positive 182 watts per square meter. So that means that I'm also in the positive direction, but this is causing energy to leave the wall, and it's at 182 watts per square meter. So they're not equal to each other. The first law says that the rate of change of energy in the element is equal to En minus E out plus Eg. Well, the problem doesn't provide us for any information about volumetric heat generation, so we're going to assume that's 0. And so what we end up with is 200 minus 182 plus 0 equals 18 watts per square meter. So what that's basically telling us is that the amount of energy within every 1 square meter of the wall is increasing at 18 joules per second. Now I want to be very clear about this. For this wall, we're assuming I'm taking 1 square meter of the wall, but that 1 square meter is 0.3 meters thick. So if you were going to calculate a volumetric energy rate, it's not per 1 cubic meter, it's 1 square meter times 0.3. So it's 0.3 cubic meters. So within every 0.3 cubic meters of this wall, the wall is increasing, the temperature or the energy in the wall is increasing at a rate of 18 joules per second. All right, so just be clear on that. Now, the last thing it says is that the cold surface is characterized by a convective boundary condition. So what they're telling us is that the outside surface, the free stream condition is 100 degrees. So we have that. We have T2. Right? We know what the wall temperature is on the right-hand wall, and we know how much energy must be going out the right-hand wall, or has to go out the right-hand wall. So I can rearrange this, and the only unknown here is my heat convection coefficient. So I'll rearrange it, and I'll find out that for this situation, if it was happening at this instant in time, the heat transfer coefficient would have to be 4.26 watts per meter squared per Kelvin. All right, so that gives us a kind of a quick overview of how Fourier's law is used to allow us to create the heat equation, which is a second order in space and first order in time differential equation. And we've looked at applying boundary conditions, or at least just the boundary conditions. So it's a second order spatial, so we need 2 boundary conditions. And we've looked at least one example of the steady state case.